Now, in this video, we will look at the question why the electron configuration of potassium is 2881 and not 289, and that of calcium is 2882 and not 2810. And yet, the maximum number of electrons that the third shell of an atom can take is 18. Now, we'll be guided by the formula 2n squared, where n is the alphabetical designation of the principal quantum energy shell. So if we want to determine the maximum number of electrons for any particular shell, we replace n with that shell number. Now, the innermost shell is the shell number 1. It is also known as the K shell. Now, the second shell is also known as the L shell. Now, this is the third shell, and lastly, the fourth shell over here in the picture. So if we want to determine the maximum number of electrons for the third shell, we replace n with 3. So when n is 3, the maximum number of electrons that shell can take is 18 electrons. So why then is the electron configuration of potassium not 289, but rather 2881, and that of calcium not 2810? But rather 2882, because the maximum number of electrons that the third shell can take is 18. Now, earlier science makes us to believe that the electrons are located on a fixed pathway and orbiting the nucleus of the atom. But in modern science, following the Schrödinger model, electrons are located in orbitals, which are spaces or regions around the nucleus with a high probability of finding an electron. It is important to note that the dual nature of an electron, that is to say, it behaves both as a particle and as a wave. And because of that, it makes it very difficult to point out the exact location around the nucleus where you're going to find the electron. In other words, the momentum and the position of an electron at any particular point in time is almost an impossibility to define with precision. However, if you choose to take a density plot of the movement of an electron around the nucleus, and you create that density plot, a region around the nucleus is going to be seen, is going to emerge, and that particular region created by the density plot, which emerges with a particular shape, is considered to be what is known as the orbital. That is to say, the area or the region around the nucleus with a high probability of finding an electron. So in modern science, electrons are no longer considered to be found in a fixed pathway or to be found in orbits, but rather they are considered to be found in a particular region, a particular area. And that particular area or region is what is known as orbitals. So regarding the position of an electron in modern science, the focus is on its sub-energy level. Now, the alphabetical designation of the sub-energy level is L. And L is associated with numbers which defines the shape of the orbital. So when L is 0, we're referring to the s orbital, which takes a maximum of 2 electrons. When L is 1, we're referring to the p orbital, which is a degenerate orbital of 3, which can take a maximum of 6 electrons. The s orbital can take a maximum of 2 electrons. When L is 2, we're referring to the d orbital, which is a degenerate orbital of 5 and can take a maximum of 10 electrons. And when L is 3, we're referring to the f orbital, which is a degenerate orbital of 7 and which can take a maximum of 14 electrons. Orbitals are of different shapes and different sizes. Now, the s orbital is spherical in shape, the p orbital has a dumbbell shape, the d orbital has a double dumbbell shape, and the f orbital has a rather very complex shape. That will not be the focus of our video for today. And these different shapes of these orbitals can be associated with different potential energies. Now, the further you go away from the nucleus, the higher the energy level of the shell. Now, the fourth shell has a higher energy level compared to the third, the third shell a higher energy level compared to the second, and the second principal quantum energy shell has a higher energy level compared to the first energy shell, which is the lowest and the closest to the nucleus. Now, each principal quantum energy shell relates to one or more sub-energy shells. The first shell, also known as the K shell, has one sub-energy shell, the s orbital. The second shell, which is also known as the L shell, has two orbitals. The third, known as the M shell, has three orbitals. The fourth energy shell, known as the N shell, has four orbitals. So for the purposes of this video, we're going to stop at the fourth energy shell. We could have the fifth energy shell, the sixth energy shell, and so on. In populating the orbitals, the lowest energy shell orbitals are filled first before orbitals with higher energy levels are filled. So in this order, as shown in the arrows, the orbitals will be filled. And we should remember that lower energy orbitals are filled completely before higher energy level orbitals are filled. So for potassium, which has 19 electrons, lower energy levels will be filled first before higher energy levels, in this manner. So for potassium, which has 19 electrons, we have 2 electrons in the first shell, 8 electrons in the second shell, another 8 electrons in the third shell, then 1 electron in the fourth shell. Now, one would observe that the s orbital in the fourth shell is filled before the d orbital in the third shell. Why is that so? Now, we should be familiar with this rule, the N plus L rule. Now, the N and the L are the alphabetical designations of the principal quantum energy shell and the sub-energy shell. The lower the value of this summation, the lower the energy level of that orbital. So if we are to compare the 4s orbital and the 3d orbital to find out the one with the lower energy level, we would be guided by this rule. Now, for the 4s orbital, it means that the s orbital is in the fourth shell. So n is 4. And the numerical designation of the s orbital is 0. So we can evaluate the n plus 1 value, which is 4 plus 0, which is 4. And for the 3d orbital, n is 3, and the numerical designation of the d orbital is 2. So if we are to compare the 4s orbital with the 3d orbital in terms of its energy level, we would realize that the 4s orbital, guided by the n plus L rule, has a lower value compared to the 3d orbital. So the 4s orbital will be filled first before the 3d orbital. And so the electron configuration of potassium will be written as So that is the electron configuration of potassium. Now, if we are to go one step further to find the electron configuration of calcium, calcium is the 20th element on the periodic table. And so with calcium, it would require adding 1 electron to the 4s orbital to get this. And that will mean that the electron configuration would change to 2882. So calcium, which is the 20th element, would have the electron configuration of 1s2, 2s2, 2p6, 3p6, and 4s2. So that is the electron configuration of potassium, which is the 19th element, and calcium, which is the 20th element on the periodic table. So you realize that with calcium, we have 2 electrons in the first shell, 8 electrons in the second shell, another 8 electrons in the third shell, and 1 electron in the fourth shell. So you can see that from the exponents over here with the first shell, which has 2 electrons. With the second shell, we have 8 electrons in the second shell. We have another 8 electrons in the third shell and 1 electron in the fourth shell. And with calcium also, we have 2 electrons in the first shell. We have 8 electrons in the second shell, another 8 electrons in the third shell, and 2 electrons in the fourth shell. And the number of electrons in the shells can be seen from the exponents. So the second shell has 8 electrons, the third shell has 8 electrons, and the fourth shell for calcium has 2 electrons. And so from here, we say that the electron configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, which translates into 2881. And calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, which translates into 2882. So this is the end of my video. Thank you very much for watching, but keep watching.